Recording, start recording. Okay, so this is going to be recorded. Oh, what is this one? So, and because we're no longer in the live events, if you ask questions, now you can actually unmute yourself and ask questions. But if you do so, know that it's being recorded. So I assume that you consent the video being posted later on online. Otherwise, just use the chat to ask your questions. Okay, great. So let's get it started. So we were talking about uniprocessor scheduling. The last scheduler we saw was the lottery scheduling. Just to remind everybody what it was. So with lottery scheduling, we gave everybody some number of lottery tickets, and then we started every round by drawing a random ticket. Whoever owns that ticket gets to run. Now, on average, on a long period of time, we would expect each thread or each task to get to run on the CPU proportionally to the number of tickets that they have. Now, we saw that the amount of time that each thread gets on CPU depends on who else is in the system, obviously, because as the number of lottery tickets change, then the probability of me being selected as the winner changes as well. Now, the last thing that we want to talk about lottery scheduling is the fact that it's random could also mean some disadvantage. And this manifests itself in unfairness. If you, let's say that we're tossing a coin and the coin comes head with probability half and comes tail with probability half. Now, if I try to toss the coin 10 times, so let's start with two draws. Let's say that this doesn't have battery. Okay, so if I try tossing the coin twice, it could well be that in both cases I see heads, or it could be that in both cases I see heads. There's no guarantee that I'm going to see one head and one tail. Now, if I increase this to 10, if I draw 10 random samples from this coin, then with high probability, I'm going to see 7 or 8 heads and 3 or 4 tails, or vice versa. Now, if I do this for 1 million times, then I should probably see about 500,000 times heads and 500,000 times tails. Now, what I just described happens with lottery scheduling as well. If you're drawing this lottery only few times, then you should not expect to see the average behavior. If you draw lottery thousands of times, hundreds of thousands of times, then you can start seeing that average behavior. Now, here is, in this slide, I'm showing you two applications running. So I have two applications, and I'm assuming that both of them have the same amount of lotteries. So it's very similar to that coin toss, 50% one, 50% the other one. Now, if the length of these two applications, these two threads, these two tasks is short, then I'm going to draw lottery really, I'm going to draw a few lotteries, right? Let's say each timestamp is 1 second, and let's say the length of a job is, I don't know, 5 seconds. Then I'm going to draw 5 lotteries for each one of them to finish. And in total, I'm going to draw 10 lotteries. Now, if I look at the finish time of the first one and divide it by the finish time of the second one, that would be a notion of unfairness. So if this is 1, so if finish time of one is equal to finish time of the other, then the system is completely fair because they had same lotteries and they finished almost the same time. If this unfairness metric that I just defined is less than 1, then it means that it's not fair. So the smaller this unfairness metric is, the more unfair your allocation is. Now, you can see this graph shows this unfairness on y-axis. So on y-axis, I have unfairness. And on x-axis, I have the job length. Now, the longer my jobs are, the more lottery draws I'm going to be having. So it's going to go to that, what I just said, 1 million draws or 10,000 draws. So as I get more and more draws, I will see the average behavior. So in average behavior, I want both of them to get the same amount of time on CPU. And if that's true, then they will finish at the same time because I'm assuming that both of them have the same length. But if the job length is small, if jobs are short, then I'm going to draw only few. And if I draw only few, then I'm going to be in the domain where I was talking about this tossing this coin 10 times. Probably, I'm going to see 6 heads and 4 tails. So one of them is going to finish earlier than the other. So that's that. So this lottery scheduling is fair on average, but if you really want to see the average behavior, you have to draw a lot of samples. Otherwise, you will have high variance, and that high variance shows itself in unfairness. To solve this problem with lottery scheduling, we switch gears to the stride scheduling. So stride scheduling wants to keep the good things about lottery scheduling, but then solve this one bad thing, which is this variance and this unfairness. So how does stride scheduling work? So in the good thing that we want to keep from lottery scheduling is we want tasks to get time on CPU proportional to their weight, their number of tickets, their priorities, whatever you name it, right? So we want them to get proportional time on CPU. To do this, we define this notion of a stride for each for the system. So what is the stride? So the stride for each thread is this big number W. Apparently, this people don't understand. So this is just a W that is a big number. So this W is a big number. Let's assume it's 10,000. And this Ni is the number of lottery tickets that each thread has. So let's run this example. So let's assume that I have 3 tasks, A, B, C. Let's say A has 100 lottery tickets, B has 50 lottery tickets, and C has 250 lottery tickets. Now we're just looking at this. What we want scheduling to achieve is I want the CPU time that A gets to be twice as much as the CPU time that B gets, because A has twice as many lottery tickets as B has. And I want C to get 5 times more CPU time than B, because C has 5 times more lottery tickets than B. So if let's say task B gets 1 second on CPU, I want task C to get 5 seconds, and I want task A to get 2 seconds. So this means that every 8 seconds, I want to run task B once, task A twice, and task C 5 times. Now, to achieve that, I'm going to use this as stride. So let's see, a stride for A is, it's going to be 10,000 divided by 100. So it's going to be 100, as you can see. A stride for B is going to be 200. Stride for C is going to be it's going to be 40. So as you can see, it's just the inverse. So the more lottery tickets you have, the lower your stride is, the smaller your stride is. C had the most number, the highest number of lottery tickets. Its stride is the smallest. Okay, so how are we going to use this stride? We're going to define this variable called pass. So this is a counter for each thread that we're going to just maintain as we go. How are we going to use this? So every time that a thread runs on CPU, we're going to add a stride to its pass. So every time a task runs, we're going to say pass equals pass plus a stride of that thread, whatever thread that is. So pass I is going to become pass I plus SI. So we're going to do this every time. And we're going to, every time we want to schedule, we will pick a thread that has the lowest pass. So we always pick the thread that has the lowest pass. So let's run an example with this. Let me see. Okay. So as you remember, So SA was 100. SB was, can you guys remind me what it was? It was, SB was 200 and SC was 50. So initially, pass A is 0, pass B is 0, pass C is also 0. Let me make this more comfortable for myself to write. Okay, now let's, at this point, everybody has the same pass. All of them are 0. So we're going to pick, let's assume that the time quantum is 1 second. Now, I want to pick a thread. So everybody has the same pass. So I don't care which one I pick. Let's just randomly pick B, right? So I pick B. B runs for 1 second. After it runs, I'm going to change B's pass to B pass B equals 200. So it's going to be whatever it was plus the stride. So the stride for B is 200, so pass becomes 200. So this is time 1. This happened at time 1. Now I go to time 2. Now A and C has pass equals 0. So we're going to randomly pick one of them because both of them have the same. So let's assume that I pick A. So I pick A. After I pick A, pass A is going to become 100. Because I'm going to get pass A plus 100, that's 100. Okay, now I go to time 3. Now the winner is clear. So C has the lowest pass, which is 0. So I'm going to pick C, and I'm going to add the stride to the pass. So I'm going to run C, and then the pass for C is going to become 50. Now I go to time 4. Which one has the lowest pass? It's going to be task C. So I will run C again, and I add the stride again to C. Okay, now I'm back to having 2 tasks with equal passes. A's pass is 100, C's pass is also 100. Okay, so we're going to randomly choose between the 2. Let's say again I choose A. So I'm going to run A. So we go time 5. We run A, pass A, becomes 200. Now, you can just run this and see that I'm going to pick C here again. C becomes 150. And then times 7, pass C becomes 200. Did I make a mistake? 5. What did I miss? Oh, sorry, it was 40. I made a mistake. So this guy was 40, not 50. I'm like, why is this happening? So, right? Am I making a mistake? No, it was 40. So let's make it. Yeah. So this is gonna be 40. This is gonna be 80. And at this point, we're not gonna do A. So sorry about that. So at time 5, we're still gonna run C. So pass C becomes 120. Now at this time, we're gonna switch to A. Pass A becomes 200. And then at 7, we come back, we do C, it becomes 160. And then at time 8, it becomes pass C equals 200. Okay, so let's look at it again. What happened? So during 8 seconds, how many times did we run task C? We ran task C 5 times. How many times did we run task B? We ran task B 1 time. And how many times did we run task A? We ran task A 2 times. And as you can see, this is exactly the same proportion that we wanted, because it actually reflects their tokens or their lotteries, right? So that's basically what stride scheduling does. So to summarize, we defined the stride, we defined pass, we added the stride to pass every time we ran our thread on the or our task on the CPU, and every time we want to make a scheduling decision, we pick a task with the lowest pass. Okay, so that's that. This the stride scheduling achieves the proportional sharing without the disadvantage that the lottery scheduling had. The lottery scheduling disadvantage was randomness and the variance. With a stride scheduling, we just get rid of that variance. Okay.
Hi, Professor. I had a question.
Go ahead.
What happens on a tie when we're doing stride scheduling?
You can just randomly pick, or you can have a predefined order and go based on that.
Okay, got it. Thank you.
Okay, so okay, yeah. I guess I saw the questions. So Peter is asking, does the scheduler choose any task when the passes are equal, or must it yeah, so when passes are equal, you just pick randomly between them. Okay. So how many schedulings have we seen so far? I think this was the 8th, so we're going to go 9. So the next scheduling policy we're going to talk about is max-min fairness. Probably some of you have heard of it. So what is max-min fairness? So the idea for max-min fairness is very simple. So we want to keep track of how much time each task has had on CPU. And every time we want to make a scheduling decision, we're going to pick a task that has had the minimum amount of time, accumulated amount of time over, from when we started the system. We want to just make sure that everybody gets the same amount of CPU. So this is a scheduling policy. As you can see, the fairness is here. It's just to ensure fairness. Now, this, if you really want to implement this, it's going to be painful. Why? Because let's say I have 3 tasks in my system, and I start with nobody has had any time on CPU. Now, let's say I randomly pick one of them, and I start running. Now, after I execute one instruction from one of them, let's say T1, now all of a sudden T1 has had more time on CPU than T2 and T3. So I have to immediately context switch to T2 and probably run one instruction from T2, and then immediately context switch to T3 and run one instruction from T3, and so on and so forth. This is the best way I can make sure that I theoretically have this equal time on CPU. And as you can see, this is absolutely not practical. Now, alternative to this is a notion of relaxed max-min fairness, which is approximation of the max-min fairness. It says, look, you don't need to really get them all have equal times. You can just have those time quanta that we talked about, and every time you want to schedule the next task, pick the one with the lowest time so far. So this prevents us from, context switching after every instruction. So we let a task run for a time quantum. The task could actually finish before the time quantum expires. The task could go for I/O, or the task could consume all of its time quantum. And once that time quantum is done, then I make a new scheduling decision. So here is an example. Let's say at the moment we want to schedule a task for the next time quantum. So we look at the cumulative CPU time that each task has had on the system. In this case, T2 has the lowest. So I pick T2. I let T2 run for a fixed time quantum. Now that time quantum expires. I want to go to the next one. So again, I look at the cumulative time. Again, T2 is the lowest. So I pick T2 and I let T2 run for another time quantum. Now, next time I want to make a decision, now T3 is the minimum. So I pick T3 and I let the T3 run. And this continues, right? So I got a question here. Is the goal of max-min fairness to minimize a starvation? It's basically the goal is to maximize fairness. Whatever fairness means here is basically the time on CPU is the metric of fairness. Now, one could argue this is not a good metric, but the goal of max-min fairness is to equalize the time that each task gets on CPU. Because every time we're going to pick the one with the lowest accumulated time, and we're going to let that task run. And by doing so, we increase the minimum. So we're just maximizing the minimum time that people have gotten on CPU. Now, what's the problem with this? So the problem with this is what happens if you have a lot of tasks? So if you have a lot of tasks in your system, let's say 1,000, 1 million tasks, this becomes round robin, right? This just becomes round robin. You're going to pick one, give it some CPU, go to the next one, and you're not going to come back to this first one until you're done with everybody else. And then you're going to come back to this one. And we should remember from round robin that round robin is really bad for response time. So it's not going to be a good scheduling if you really care about response time. Now, one thing that we can do, which I sort of mentioned, at the beginning of the I think it was 2 lectures ago when I was talking about round robin, I mentioned that you don't need to have a fixed time quantum when you're running round robin. So the idea is to modify max-min fairness with dynamically changing time quanta. So what's the idea here? The idea is, let's define a target latency. Now, this target latency is the time, it's an interval that we want each task to at least get to run on the CPU once. So, you know, think about it intuitively. If I say my target latency is 20 milliseconds, what I mean by this is that I want each one of my tasks to run at least once every 20 milliseconds. So whatever your target latency is, you want all your tasks to run at least once during this this period. Now, what does this mean? It means that if you have n tasks, then you should set your time quantum, the size of your time quantum, to be equal to this target latency divided by the number of tasks that you have. So if my target latency is 20 milliseconds and I have 4 threads, then my time quantum should be 5 milliseconds, because by the time I come back to the first task, 20 milliseconds has passed. So every 20 milliseconds, each task gets to run once. Now, the problem with this is we're still not addressing the issue. If I have so many tasks, let's say I have 200 tasks, then dividing 20 milliseconds to 200 gives us 0.1 millisecond. Now, 0.1 millisecond, it means that I have to context switch every 0.1 millisecond. And if you remember, context switching has overhead. And there is a possibility that the overhead of of context switching becomes equal to your time quantum. So you might get to a situation where your time quantum is, let's say, some number x microseconds, and then you pay the same amount of time to context switch. So let's call this one delta. So in this situation, your overhead is 100%. So you do some useful work here. You're running one of your tasks, but then you spend the same amount of time to context switch between your tasks until you start the next one. As I said previously, what we want is the delta over x to be really less than 1/10. So that's pretty much what we want to shoot for. So if they're equal, then this ratio is half, and that's really bad. It's kind of like 100% overhead. So to fix this one, what we're going to do is we're going to define this minimum granularity. Now, minimum granularity is how small could this time quantum become. So we're going to say that the length of time quantum should be maximum of target latency. Sorry for my handwriting, it's not a comfortable position. Let me change it. So target latency divided by n, and this minimum granularity. So let's say if my minimum granularity is 1 millisecond, this means that I don't want my time quantum to be less than 1 millisecond. Then if n equals 200 and target latency equals 20, then this becomes 0.1 millisecond. But then I'm going to pick the maximum of the two. So I'm going to pick this one millisecond. So I don't allow my time quantum to be less than 1 millisecond. And this will basically, what happens with this is that I don't pay a lot of overhead, but I can't meet the target latency. So I'm somewhere in between. I try my best to stick to the the target latency, but I have a hard constraint, which is the overhead of context switching. So I pick the middle ground. Okay, so now the next extension to max-min. So let's remind ourselves where we started. There was the theoretical max-min, which we said is not practical. Then we talked about approximate max-min, which was the introduction of time quantum. Then we said, what about latency? Then we had max-min fairness with dynamic time quanta. Now, the next extension we want to add to max-min, and by the way, where I'm going with this is the Linux scheduler today. So we're going to get this theoretical max-min and get it as close as possible to today's Linux scheduler. The next stop is weighted max-min fairness. What if, similar to lottery scheduling, similar to stride scheduling, I don't want to equalize the time on CPU? What if I want to have some what's called some weights, some lottery, the equivalent of lottery in my system? What if one task should get twice as much as the other one? What if one task should get 3 times more CPU than the other one? So to integrate that, we're going to talk about weighted max-min fairness. So we're going to add weights. So if you ask me what these weights are, these are kind of like those lottery tickets. So the higher your lottery tickets are, the higher your weight is. You can actually think about the number of lottery tickets that you have as your weight. So that's your weight. The more you have, the higher your scheduling, the more time you get on CPU. So how can we integrate that notion in our max-min fairness? So the way we're going to do this, the key idea is to use the weights to change the time quantum. So max-min fairness has 2 main ideas. The first one is to change the time quantum per task for given weights. The way we're going to do it, so just a reminder, so this is what we saw in previous slide. So this is a dynamic time quantum, but it's fixed for everyone. So everybody gets the same time quantum. Now, if tasks have weights, then we can change the time quantum to be task specific. So for task I, the time quantum is equal to weight of task I times this target latency divided by the sum of weights. Now, let's go from here to here. How can we go from Qi to Q? If everybody's weight is equal, let's say Wi is 1 for everyone, or W1 is 2 for everyone, it doesn't matter. If Wi is equal for everyone, then this sum is basically n times Wi. And then I can just cancel Wi's, and I'm going to go back to this target latency divided by n. So this new weighted max-min fairness is a superclass of the max-min fairness we talked. And the superset comes from the fact that it also covers the case where everybody has the same weight. So if everybody has the same weight, then everybody's time quantum size is the same, and it's equal to target latency divided by n. But if tasks have different weights, then their time quantum is going to be different. Let's say you have 2 tasks in the system. One of them has weight 2, so W1 is 2 and W2 is 1. So let's assume that's the case. then Q1 is going to be 2 times target latency divided by 3. And Q2 is going to be 1 times target latency divided by 3. So as you can see, Q1, the time quantum for task 1, is twice as much as Q2, because Q2 is 1/3 of the target latency, but Q1 is 2/3 of the target latency. So this is the first idea we're going to use. So the first tweak that we're going to add is to make everybody have its own specialized time quantum, Qi. So here is an example. So let's assume that I have two tasks, A and B, and let's assume that target latency is 20 millisecond, and minimum granularity is 1 millisecond. And I have two threads, A with weight 1 and B with weight 4. So every time you see these, you should think about what should happen. So for every 1 second that A gets, I want B to get 4 seconds. That's what these weights mean. The actual value of weight doesn't matter. It's just the ratio between weights that matters. So if you just use the equation that is in front of you, you can see that the time quantum for A becomes 4 milliseconds in this setting, and the time quantum for B becomes 16 milliseconds. So A's time quantum is going to be 4 times smaller or shorter than B's time quantum. So this was the first tweak. The second tweak we're going to use is the notion of virtual runtime. Now, this is compared to actual runtime. If you remember with MaxMax Fairness, when we started, we wanted to make sure that everybody gets the same amount of time, actual time on CPU. Now, with weighted MaxMax Fairness, we're going to look at virtual time rather than the actual time. Now, how do we define virtual time? So the virtual time is going to be the actual time divided by weight. So virtual time is going to be actual time divided by weight. Okay, so the higher your weight is, the slower your virtual time progresses, right? Because this guy gets higher, then you need more actual time on CPU for your virtual time to increase. Now, the lower your weight is, let's say your weight is 1, then your virtual time is equal to actual time. If weight is 2, then your virtual time is half of the actual time. So that should give you the sense of what this is. Now, let me see if I have the example. So let me switch back to my notes and run another example similar to the example that we ran with stride scheduling. Let's say we have two tasks, A and B. So A's weight was 1. So this is weight of A. Back to comfortable setting. So weight for A is 1. Weight for B is 4. Now we saw that QA in our example, how much was it? QA was 4, QB was 16. Okay. So QA was 4 millisecond, QB was, gosh, my memory is so bad, was 16 millisecond. Okay, So we start with virtual time for both of them 0. VA and VB, both of them are 0, right? So virtual time, we start with 0. At any given time, we're going to pick the task with the lowest virtual time. Now, at this point, both of them are equal. So as always, let's randomize. And let's assume that I randomize and I pick A. So I'm going to run A for 4 microseconds. So the first microsecond, the second microsecond to the 4th microsecond. So from time 1 to 4, I'm going to run A. And after this, virtual time of A becomes what it was, which is 0, plus the actual time that A got on CPU, which is 4 microseconds, divided by the wait. So it's going to be 4 microseconds divided by 1, because weight of A is 1. So this is equal to 4. Okay, so at this point, I want to make another decision. So VA is 4, VB is 0. So I'm going to pick B, right? And I'm going to run B now for 16 milliseconds, because the time quantum of B is 16 milliseconds. So from time 4 to time 20, I'm going to be running B. And after that, VB equals 0 plus. Now, B ran actual time for 16 milliseconds. So 16. But the weight of B is 4. So I'm going to divide by 4. So I'm going to get 4 again. Now I'm in the situation that both of them have equal virtual time. So again, I'm going to toss a random coin, and probably either I will pick A or B. It doesn't matter. Now, the end result, however, if you look, now 20 milliseconds has passed. As you can see, I ran A for 4 microseconds, and I ran B for 16 microseconds. So the time A got on CPU is 1/4 of the time that B got on CPU. And that's exactly what we wanted, right? So we're equalizing the virtual times. You can see that if we were to equalize actual time, then at this point, the actual time of A, so actual time of A is 4, actual time of B is 16. If we wanted to equalize actual time, we would have now prioritized A. We would have given A CPU again. But that's not what we want to do. Instead, we're going to use the virtual time to schedule. So that's where we divide by the weight. Okay, so somebody's asking, why is MaxMax Fairness better than stride scheduling? That's a good question. So let's actually compare. What's the difference between stride scheduling and, so I guess now you can see them both back to back. So this is a stride. This is weighted MaxMax Fairness. The main difference that these two have is that in a stride scheduling, we have the same time quantum. So the time quantum is fixed. So everybody has the same time quantum. Whereas in MaxMax Fairness, in weighted MaxMax Fairness, we're changing the time quantum dynamically for each task. So each task has its own time quantum. Now, if you ask me which one is better, MaxMax Fairness could achieve lower overheads, so better throughput. The reason is we're context switching less. So as you can see here, we had to, when we were running this task A, B, and C, we had to run A, context switch to B, and then, context switch to A, and then come back and run the rest of A. But in MaxMax Fairness, you get to run your entire time quantum at once. So you're going to have less number of lower number of context switches, and that's better. So because context switching has overhead, so we pay lower overhead in MaxMax Fairness because people have different time quanta, and if your weight is higher, you get to run for a longer period of time on the CPU. But other than that, both of them achieve the same goal. So both stride scheduling and weighted MaxMax Fairness, both of them achieve the same goal, which is they allocate CPU time in proportion to tasks' weights. But as you can see, they have different approaches. In a stride scheduling, we have fixed time quantum, and we had to use this notion of pass. In MaxMax Fairness, we have per task time quantum, and we have a notion of virtual time. But they're very similar. So the notion of pass is very similar to the notion of virtual time. OK. So going back, so that's that. So we talked about that. Now, that's it. I'm not going to show you any more scheduling policies. We're done with the scheduling policies. So a little bit of just housekeeping about all of these scheduling policies that I talked. Oh, one thing. So this last one that I talked about, weighted MaxMax Fairness, is very, very close to the Linux CFS scheduler. So the idea of CFS is exactly weighted MaxMax Fairness, although, if you look at the actual implementation, it has so many more things. In particular, one of the important pieces of CFS is for multiprocessors. What happens? So in this case, all the examples that we talked, we had a single CPU. So if task A runs, then task B is not running. And if task B is running, then A is not running. But if you have a multiprocessor, then both of them can run, right? So let's assume that I have these two tasks, A and B, and I have two CPUs, and A's weight is lower than B. Sorry, A's weight is higher, whatever it was. I think A's weight was lower than B. But if I have two CPUs, who cares? I can run both of them, and both of them can have equal time on the CPU. So anyhow, things get a little bit tricky when you have multiple processors. So if you are interested, I suggest that you look at let me see. So I guess it was, I put the paper. So if you're interested to know more, unfortunately, I won't have time to cover multiprocessors. That's really that really sucks. But if you're interested, you can watch the lectures from ECE. So watch the multiprocessor scheduling from ECE 350. The link to the website is on my own web page. You can find ECE 350 if you're interested to do the lectures. Otherwise, read this paper at the bottom of this one. So this paper, this last one here. It's an easy read. It's like, maybe it takes 1 hour, 2 hours of your time, but you will learn a lot. So this is the Linux Scheduler, a decade of wasted cores. Well-written paper, very informative. It talks about load balancing in multiprocessors. So I highly recommend, if you get a chance, definitely take a look at that paper. Okay, so now let's talk about comparing different scheduling policies. If you want to compare scheduling policies, you have different choices. The way you can compare. The first one is deterministic modeling. You can, if your workload is deterministic, there is no randomness, and your scheduling policy doesn't have any randomness, you can model everything deterministically and study it the way you want and, you know, you compare different metrics. Usually this one is not an option because there are so many random things in the system. Usually we don't have a deterministic model of memory. We don't have a deterministic model of interrupts. We don't have deterministic model of so many things that are happening in our systems. So usually the first one is out of picture. Then the second option is to use stochastic models. So basically assume that events happen based on a distribution. So let's say you get arrival on average every 10 seconds. And let's say the distribution of execution time is exponential, or it's some other distribution. So you make some assumptions about how often tasks come to your system, how long each task takes. So you make your, you maybe study your system, you look at the histogram of your execution times, you look at the histogram of inter-arrival tasks, and you fit it with a distribution, and now you have a distributed a stochastic model. In that case, usually you can use mathematical queuing approaches to compare and mathematically model your system. And if that's available, then good for you. You could, mathematically look at average behavior of your system. Unfortunately, this second option is also very limited, and in many realistic and real-world systems, this second one is also off the table. The reason is, queuing models work if you have a single queue, but if you have a network of queues, if your task first goes to server 1, and then from server 2 goes to server 3, and then from server 3 goes back to the client, and this happens, that happens. Even in the operating system, your task starts in a ready queue, then it goes to IO queue, then it goes to some lock queue, and so on and so forth. And if you want to model all of these queues, good luck. There is no mathematically sound way of modeling this. So basically, queuing theory works, but for very simple settings. Now, if these two are not possible, then your third option is to simulate. So basically, implement your scheduling, pick a workload, and just run the system in simulation. And then study the metric that you're interested in. Let's say your throughput, your fairness, your, response time, whatever metric that you're interested in, and then compare different algorithms. So you just, implement them, you run your system, you study your system, and you draw conclusions. Now, one thing that you have to be really careful about simulation is the notion of a starvation and sample bias. So suppose that I want to compare two scheduling policies, let's say FCFS and SGF or STF. Now, one approach I can do is, after I implement both of them, I pick a set of tasks, right? Let's say it's an infinite sequence of tasks. I create it, I fix it, and I start feeding it to my system. I start at some time, so I set the timer. I say, ding, I'm going to start simulating. So then I run both of the systems, and then at some stop point, I stop my simulations, and then I look at the metric that I'm interested in. Let's say the response time of my system. How do I calculate the response time? Well, I look at the response time of tasks that ran in the first system with, let's say, FCFS, and then I look at the average response time of the tasks that were executed in SGF system, and then I compare them. So is there any issue with this comparison? So basically, I ran both of the systems for the same amount of time, and then I looked at the tasks, and I'm comparing these metrics. By the way, very high chance, if any of you goes to industry and you're assigned, some task to study performance of the system, the backbone. Go and see what is the bottleneck, what is happening in the system. You're going to do something like this with high probability. So pay attention. You might then come up with alternatives, and then comparing your alternatives, you might actually do this, right? You study the system, you implement the alternative, and then you compare. Now, there's a problem with this, and the problem is you are comparing oranges and apples, right? Because the tasks that run, let's say, with FCFS are different from the tasks that run with SGF, for example. Now, let's assume that your workload has one big task, one small task, one big task, one small task, one big task, one small task. With FCFS, after a given time, you're going to be running one small, one big, one small, one big, one small, one big, because it's FCFS. What about SGF? In SGF, all the big ones are going to be queued because you get a small task, and you're going to prioritize the small task, and you're going to run the small task. So although you run both of the systems for the same amount of time, at the end, when you stop, you're going to look at different sets of tasks that have been executed. And if you look at the response time of the tasks in under FCFS, you might actually draw wrong conclusions. And by the way, this actually happened to me and my grad students very recently. We were writing this paper, and we were comparing ourselves with the state of the art in the literature, and we were so confused. Our system on paper looked a lot better than their system. And when we were looking at the numbers, we were getting really bad numbers compared to the numbers that they got. And turned out that they were doing exactly like this. And interestingly, the scheduling policy that we had in our system was FCFS. And the scheduling policy that those guys had was something like SGF. Of course, at this point, you should know that SGF is not possible, but it was something close to that. And what was happening was these guys, the paper that we were comparing against, was looking at a specific set of tasks, and it was reporting the response time for that specific set of tasks. And it was ignoring the other tasks. Whereas in our system, we were looking at everybody. So it turned out that these guys were starving the long tasks. And that's why their numbers were good. But we were running all of them. We were running the small tasks and the big tasks. Our numbers were higher than the other paper, but we were more fair because we weren't starving anyone. So this actually happens. Now, how can you get rid of this? How can you fix this in your comparison? One way to do this is, instead of having simulating the system for the fixed amount of time, let's say I start my system and then I end. Instead, you can simulate the system for a fixed number of tasks. So you can say, I'm going to assign number to my task. So this is the first task in the system until this is like, task number 1 million. And I can start my simulations and end my simulations when a specific number of tasks are done, or a specific set of tasks are done. So let's say I'm interested in the first 100,000 tasks. So I run simulation as long as needed, so that all first 100,000 tasks are executed. And at that time, I stop. Now, it could be that different systems run this for different periods of time. Maybe FCFS takes X amount of time and SGF takes some other amount of time. Interestingly, in the setting, specifically for SGF, it could run forever and never finish because all the long tasks are starved. And in the system that we simulated, we made this comparison this way. So we said, okay, we're not going to compare ourselves with the numbers that they reported. We're going to compare in a fair way and look at all the tasks that we run and all the tasks that they run. And turned out that their system was really bad. I didn't want to use the CRAP, but their system was really bad. So anyhow, so this is one way of doing it. And then you can, once the simulation is done, you can look at the average response time among those tasks that are common in both cases. So that the first 100,000 tasks that have been executed in under scenario 1 and scenario 2, and then now you have a fair comparison. So this actually sits very, very much well with my experience, at least. So to conclude, we have talked about so many different scheduling policies, I think 9, and then the last one, the MaxMax Fairness, had a bunch of extensions. But then each one of them is good for something, right? You can't have one that is good for everything. So depending on what you really want from your system, you have to choose between these scheduling policies. And these scheduling policies, if you're going to be a computer software engineer, they will come back again and again and again and again in different contexts, in distributed systems, in parallel computing, in operating systems, sometimes even in computer architecture. But you know, just know which one is good for what. Okay, so that's that. Because I started this lecture 15 minutes late, if you guys don't mind, I'm gonna continue for 10 more minutes. So I will go until 4. So if you want to log off, feel free, because it's gonna be recorded. So I will post the recording. Hopefully it's being recorded. I assume it's being recorded because it said that it started recording it. So let me see. I don't know where to go. Anyhow, it's probably being recorded. So, and if not, then I will post the same lecture from EC 350. So don't worry, we'll get you covered. Okay, so next topic is going to be, this one is off. Okay, so where the heck is? Okay, so SE350. Oh, this is not. What can I refresh? Oh, now we're talking. Okay. So we're going to move to address translation for the remaining 13 minutes. I'm going to talk about that. Okay, download it. Okay, so we're going to talk about memory for the few coming lectures. And so this is, you can think of this as the third part of the course. First part being the operating system concepts, second part being CPU scheduling, and now the third part of the course is memory management. Now, similar to CPU, the memory is also limited. So the same way that we have, you know, so far with the scheduling, we were talking about a single CPU that you're going to share between multiple threads. The same happens with memory. So memory is also limited. So your physical memory is 4 GB, like, you know, 16 GB, at most 32 GB, and you want to allocate that between your threads. So the illusion that we want to provide is that each task has unlimited memory, almost unlimited, because if you look at, virtual memory, which is what tasks think they have, it's all their address space. It's really huge. So we can say that's infinite. So that we want to make sure that everybody thinks that that's what they have. In reality, however, we have limited memory. So we have to kind of make that illusion, create that illusion with the limited resources that we have. So that's the job of the operating system. Now, the same way that with the scheduling, we started multiplexing the CPU for our tasks, with memory management, we're going to multiplex memory for our threads and our processes. Now, what are the goals of memory management? The first goal of memory management is protection. So we want to make sure that processes are isolated from each other. So one process cannot access the other process's data. We also want to protect the operating system from other threats. So protecting threats from each other, and then protecting operating system from threats. Now, this could mean that we need some access control. So we want to give special accesses to certain processes. Maybe one process can read this memory location, and other processes can read and write, or maybe everybody can just read, so on and so forth, or maybe somebody should not have access. So we want to give a special access to different areas of our memory to different processes. The other thing that we might actually want to do, which is kind of like against everything that I just talked about against isolation, is sharing data. So we don't want the system to be too restricted that processes cannot share data. We want processes to be able to share data. So what are the scenarios that sharing data comes into play? So one is basically if you have shared libraries, right? If you have, so shared libraries is the end of it in my examples. Let's say everybody is using clib. So you really don't want to have multiple copies of clib in your memory, because that would be a waste. So you have a single clib in your memory, and you want everybody to share this. The other opportunity for sharing is shared binary files. So an example being fork, right? When you fork a process, the child uses the same binary than the parents. So both of them share the same binary. So it would be a waste if I duplicate the binary for the child. And so being able to share that binary between the child process and the parent process is means efficiency. It means less waste. Another example is inter-process communication. If you remember, we talked about shared memory as a way for different processes to communicate with each other. So here we are. What are if we want to design a system to manage memory, we should be able to provide sharing because it's useful for different processes to share memory. The last example I have here is memory mapping files. So I don't know how many of you have seen memory mapped files, but the idea is instead of using the system calls to read and write from your file, instead of saying, open and then read and then write, you can open your file, then map your file to memory, and then start using load and store to memory in order for you to read and write to that file. Now, you have to note that when you're using memory, it's temporary, right? So whatever changes that you make happens in the memory. So at some point when you're done with your file, you have to flush everything down to your, let's say, SSD or your hard disk. But the process is called memory mapped I/O or memory mapped filing. Now, if two different processes memory map the same file, let's say I have one file and two processes have mapped it to memory. Now, it would be a headache if I have two copies of the file in my memory. So the best way is to have one copy of the file in memory and make both of them use that same file. So the reason I spent some time to go through these examples is because these examples are very important. So make sure that you understand this. So there are multiple use cases for different processes to share the same memory. Then the second goal of memory management is allocation. So the first one is protection. The second task or the second portion of memory management is allocation. So to make a decision on who gets which memory regions, how you allocate memory is also a big piece of memory management. So this part is very close to what you did for lab 1, which was deciding to allocate memory to different tasks. In your case, in an general purpose operating system, deciding on allocating memory between different tasks. Before I dive into the specific of how we do memory management in operating system, I'm going to end this lecture with this background. Hopefully you know about this, but if you don't, it's not going to be, rocket science. So probably a reminder for many of you who have taken a computer organization course in the past. So you remember about address spaces. We talked about virtual and physical address spaces. Now, if you have k bits, you can address 2 to k different things, right? So if your address is k bits, then your address space is 2 to k times whatever length of each memory location is. But the important piece here is this notion of having k bits to address something, whatever that is, and how that blows up to exponentially to become 2 to k different things. Now, usually when you're talking about memory system, these things are bytes. So you have bytes as a unit of addressable objects in your memory. So if that's the case, let's say if I have yeah, so if I have 2 to 10 bytes, so what am I asking here? Oh, okay. So this notion of kibibyte, so I'm gonna not say kibibyte because it's so awkward to say kibibyte. Usually people say kilobyte. If I were to be super technical, it's kibibyte, so it's ki byte, because what I'm using it is 1024 bytes. But if you say kilobyte, what you mean is 1,000 bytes. So this one is kilobyte. This one is kibibyte. And 2 to 10 bytes is basically 1 kibibyte. Now, from now on, I'm going to do the mistake on purpose, and I'm going to say kilobyte, megabyte, because for megabyte, I think it's megabytes, so something. So it becomes really awkward. But anyhow, so that's one. If your address, if your memory is 4 kilobyte, and let's say the addressable unit is 1 byte, you can ask how many bits do you need to address it. So if I have 4 kilobytes, this is 2 times 2 kilobyte. And as we saw up there, 2 kilobyte is basically 2 to 10 bytes. So this becomes 2 to 11 bytes. Now, if I want to address 2 to 11 bytes, I need 11 bits. So this becomes how many bits do I need to address my memory. Oh, I made a mistake. Oh, sorry. So sorry. I made a mistake. So it's 4 times 1. So it's 4 times 1 kilobyte, and then 1 kilobyte is 2 to 10. So this becomes 2 to 12. My apologies. So then I need 12 bits. How much memory can be addressed with 20 bits, 32 bits, 64 bits? So this is your system right now. Most of your systems are 64 bits. Older systems are 32 bits. And this almost never happens, but just for the sake of argument. So if you do 2 to 20 bytes, that's basically 1 megabyte. 2 to 32 bytes is 4 gigabytes. And 2 to 64 bytes is 2 to 24 terabyte, 2 to 14 petabytes, and 2 to 4 exabyte. Oh, sorry, this one is PB bytes, but whatever that is, and then exabyte. So this basically is the virtual address space in a 64-bit system. Now I'm going to stop here. I went even more than what I promised. So hopefully from next lecture we will dive into the components of memory management. Sorry for the delay and the technical difficulty I faced. Thank you for sticking around, and those of you who are watching this offline, thank you for watching it. We'll talk to you on Thursday. Take care. Bye-bye. Oh, okay.